Good evening, everyone. It's a pleasure to welcome you all to today's session on hands-on practice of FSS development. I'm really excited to have our instructor for today, Ms. Geetanjali, who's a research scholar of Dr. Gulam sir. So today you will be learning something new. I hope you all enjoyed the session. Over to you, ma'am. You can start now.
Thank you for the introduction. We are going to design a band stop and band pass filter. So, I will share the screen. Hope my screen is visible to you all.
Yes, ma'am.
I hope you guys can understand what is meant by FSS by by Lingeshwaran sir from yesterday's session. So in this session, we are going to design a band stop and a band pass FSS for millimeter wave application. So, from the outline starts with a brief introduction of FSS and what are the different design of FSS for enhancing the bandwidth and the design of band stop FSS, design of band pass FSS, and we are going to analyze the result for angular stability, polarization stability, and shielding effectiveness. So, as Sir said from yesterday's session, so this FSS is a periodic arrangement of the patches and slots. Obviously, patch element is used to design the band stop FSS, and similarly, edged slot is used to design the band pass FSS. In recent years, they have developed band stop FSS for the shielding application and bandpass FSS for communication application. And they have also designed a multifunctional FSS with the incorporation of pin diodes to achieve the absorption and transmission characteristics. Because in FSS there is a communication blockage barrier in which the shielded system remains completely zero due to the absence of grounding mechanism. So this FSS is highly used for radar and stealth application, which is highly recommended for military defense and communication application. And they have also designed the FSS for conformal radar application. Here are some design of uh, here are some design for loop and patch structures. As explained by Lingeshwaran sir yesterday, the loop is used to design the band stop FSS and band pass FSS and for band stop FSS they have used patches. So you can see in group 3 here. Here they have designed a different type of FSS to enhance the bandwidth and also to achieve the miniaturized size. So first they have designed a convoluted FSS by using the square loop. The meander line and the convoluted square loop is used here to achieve the frequency at lower link. And for fractal based structure, this fractal based FSS is used to enhance the bandwidth for FSS and to achieve the miniaturization, so which is the main characteristic for FSS, they have used compact resonating structures to design the structure. Here are the steps that we are going to design the FSS. So first we have to construct the unit cell and we have to set the upper and the lower frequency, and to simulate the FSS we will apply the boundary condition in frequency domain. So I hope you guys can understand the ca- the icons in CST simulation. So there is a navigation tree and setup solver. So it is in both frequency and time domain, and the working plane parameter list messages and progress. So without any time delay, we can proceed for CST. I hope you guys have CST software with you right now. I want you to design parallelly with me, so we can start the design. Is my CST is visible now? Anyone? Is my CST is visible now?
Visible, visible, ma'am, visible.
So now we are going for the project template, and we have to. I want you guys to design parallelly. If you have any doubts, you can stop and ask me. And click for antennas. So you can also design the FSS by choosing periodic structure. In the session, I'm going to design the FSS by choosing antennas. Next, then planar patch. Then I'm going to choose frequency domain. So the difference between the frequency and time domain here is, if you choose the time domain, the simulation will run faster. That is the difference. Next. So I have chosen the wave frequency to design the FSS, because the FSS can be used for a radar application, as I said. So the wave region is 30 to 300 gigahertz. So I have chosen 40 to 70 gigahertz. I have to choose next. So I have chosen the higher frequency. So obviously my size is very low. So to design the FSS, you have to design the substrate first. Then you have to design the conducting layer. So now we are going to design the substrate. So let it be. So I'm going to choose the substrate as Stephanie. So I have given PS2.3 because we have chosen the higher frequency. So the periodicity should be low, and T1 is 0.5. 0.5. You can see the substrate now. So it is a rigid substrate. You can also design the FSS in conformal state based on the application. So for radar application, we have to achieve the bandwidth as much as possible. So we have chosen the rigid substrate. So the bandwidth also achieved high in conformal substrate. that is your choice. So, and you can choose the material as the availability of materials in the fabricated in the fabrication company. So next, are you guys doing parallelly? Do you have any doubts as far now?
Ma'am, could you say what is the thickness, ma'am?
So the thickness is 0.51 mm and the periodicity is 2.3. I can show you the brick. Are we done? Are we done now? Shall I continue?
Yes, ma'am.
So from yesterday's session, Sir have told a different type of loop structure. So I'm going to design a cross loop structure to design this bank stop FSS. So, Sir said that there is no particular formula to design the FSS, but I suggest that you can design the FSS by using the wavelength formula. I will show you. So you can design the resonators by using the wavelength formula. Like if you have to choose the periodicity as less than the wavelength, you have to use lambda equal to c by f as Sir said yesterday itself, and you have to calculate the dielectric constant with the corresponding operating frequency. These are the formulas you can note down or take a snap. So we can start the design for conducting layer. So this resonance structure can be designed with a wavelength of lambda by 4 or lambda by 6 to achieve the corresponding frequency that what you have fixed for the application itself. So you can design the FSS for any application. You can take the frequency standard from the FCC allocation table. There is some plenty of FCC table in Google. You can take it from that, and you can choose the application, and you can design the FSS for that particular application. So from so in past years they have designing the FSS for ISM bands and for radar application. So for ISM bands, as Sir said yesterday, they have he have chosen a very low frequency, that is 2.4 gigahertz, and also he have achieved the miniaturized size. So it is also applicable to this frequency, that is we are going to design the bandstop FSS for 50 gigahertz. So we can design the structure now. So let it be. So this design I have taken from the this design I have taken from the paper second order band stop frequency response. I can share you the link after completing the design. You can verify it. So the height should be P1 to P plus. Is it okay? You guys completed from as far now? Any doubts? Can I get any response? I hope you don't have any doubts.
Ma'am, once again, can you please say the value of T1?
Yeah. T1 is 0.51 mm. Do you guys completed? Okay. So we have design across. So now we have to rotate. So you can choose the rotate option from transform, rotate, and you have to select copy, and you can manually rotate the structure, or you can also give the value here directly. Have you guys completed? Any doubts? Um, then we will design a. So the second loop will be point 1, point 1, and point 7, and 7. Then it will be T1 to T plus T1. Have you guys completed the second loop? Can I get any response so that I can proceed further? Am I not audible?
Ma'am, could you repeat the dimensions of the inner rectangle once again?
Okay. So the x min and x max is 0.1 and y min and y max is zero point 0.7. So the height will be T1 to T plus T1. So we are placing the copper and heel on the substrate. So the Z max will be T plus T1. We have designed the inner loop. Can I proceed further? Okay, I will proceed further.
Yes, ma'am, it is clear now, ma'am.
Okay, okay. Okay, so to form a loop, we have to delete the inner cross loop. So I will select. You have to go to Boolean, subtract, solid 2, and solid. So we have got the in cross loop. So this cross loop is highly used to achieve the band stop FSS. So it is the first stage of FSS. Then we are going to design a cylindrical patch. Show here. So this is the second resonator that we will do shortly. So first we will run the square loop. So to run the FSS, you have to go for simulation, boundaries, and you have to choose unit cell. So it is a FSS, so it will reflect and transmit. So it can't be observed. So the Zmin and Zmax should be open at space. So if it is an absorber, you have to choose ET equal to 0, which is here. So as for the FSS, you have to choose open at space, and the flockade boundaries is 1. You have to choose for both Zmin and Zmax is 1. Are we clear up to now? Okay. Um, are you guys designing? I click OK. So, any doubts till now? See, it is a simulation session. You have to interact as much as possible. Any doubts? If there is no doubts, I will proceed. So, we will start the simulation. So, we see these parameters. So, we have got the resonant frequency at 56 gigahertz. So, as Sir said, the bandwidth is necessary for FSS. So, we can see the bandwidth from screen. So, the bandwidth for the structure is 52.6 to 58.8 gigahertz, which covers the millimeter wave application for radar. I hope you guys are clear up to now. Do you have any doubts till now? Are we good to go? Do you have any doubts?
Ma'am, could you repeat the subtraction alone once, ma'am?
subtraction. Select this. I have to go for the subtract. Is it clear? I have made a mistake. I have 0.25. And for the inner loop, the dimensions are 0.5. So you have to select the solid one which we have designed first, and a solid one have to so for FSS there will be no grounding mechanism due to it has to be transmit and reflect. So for in case of absorber, there will be a grounding mechanism. So comparatively, if in FSS the bandwidth enhancement is easy, uh, and other structures with ground, the bandwidth enhancement is little more difficult. So we have got the result. So this one, let it be -10. So we have got the result from 56 to 58.8. So the resonant, so it is resonating at 56.56, and the -10 dB coverage from 52.6 to 58.8, which is very high. So it almost covers the shielding of FSS. So this is first stage of designing the resonators. So the second stage will be we are going to add the second resonator. So for the to select modeling brick and just asymmetrical. So the dimension for this is 0.54 to 0.86 and 0.56 to 0.88. So the Zmin and Zmax will be T1 to T plus T. If the ground is set presented in this FSS, we have to change the height from T plus T1 to T plus T1 plus T. So as for the absence of grounding mechanism, the height will be T1 to T plus T1. And this material is copper and lead. So stop the view and select OK. So first we will just copy this result for further use. That's mean and that's max will be 0.54 to 0.86, and Ymin and Ymax will be 0.56 to 0.88. So that means the max will be T1 to T plus T1. Then, so we are designing another loop to achieve the second resonant frequency. So we are designing another loop here. Let it be 1 to 1 plus 1.1, and Ymin and Ymax will be 0.56 to 1.15, and the same height, that is T1 to T plus T1. And just put it through. Then you have to you have to connect the this this square patch and this rectangular patch. So I'm going to add a little stud in the middle of this. So this will be 0.42 T1 plus T1. Okay, so we have designed the second receiver. So I will look for 0.5 to 1.5, 1.05 to 1.5 into 10 plus 21. I hope you guys have no doubts. Do you have to repeat this step or are we clear till now? Anyone? Okay, I will just repeat the steps. So just I will show you. So the dimensions of the little square patch here is 0.542, 0.86 and 0.56 to 0.88. This height of the patch is T1 to T plus T1, and for the rectangular patch the dimensions are 1 to 1.1, 0.56 to 1.15. So the height is T1 to T plus T1, and for the little step it is 0.86 to 1, 0.56 to 0.645. So the height will be T1 to T plus T1. So now we are going to rotate these resonators. So you just have to select and click transform, use mirror. So mirror will be helpful compared to translate without any error in dimension spacing. So click mirror and go for copy and UX1 and give OK. Similarly, so we have designed a second resonator here to achieve the second frequency for the FSS, and we have mirrored these resonant structure on the other side. Now we are going to mirror the third part here. Just click any of the resonator. I have clicked solid 3. Just come to solid 4. So then again click transform and go to mirror. Similarly, so we have copied this resonator on 3 sides, and to copy it on 4 sides. So, that's it. We have designed the second resonators. So it is up to you to design the single band or dual or triple band. It's depending upon the application. So it is very uh, so it is really helpful for the bandwidth enhancement if we have designed the second frequency, and it is also helpful to achieve the desired radar frequency if there is an additional band. I hope you guys have no doubts up to this. If you have any doubts, you can ask me. I will explain you now. Do you have any doubts till this step? Any doubts? I hope you have no any doubts. So I will simulate further. So it take quite small time compared to quite a less time compared to low frequency structure because the unit size is very small. There is 2.3 mm, so it is running very quickly compared to the higher compared to the lower frequency structures. So you can also design the FSS in HFSS. So comparatively, CST is the best because it gives a more accurate result accurate result compared to the HFSS software. So you can also see the equivalent circuit model for the structure by using ADS software. You can design the filters and you can validate validate the S parameters of both CST and ADS. I hope you guys are listening. So we have achieved the dual frequency here. The one is 49 and the other one is so it is resonating at almost 50 and it is 56.41. So the first band for this FSS is 46.3 to 51 gigahertz. The second is 53.7 to 60.3 gigahertz. So we have designed the band stop FSS for both 50 and 56.4 gigahertz, which is a millimeter, which covers the frequency of millimeter wave region for radar applications. Mm, So you can see from the first step, and for the second there is a slight frequency shift on the second frequency band due to the coupling between the uh, cross loop and the patches at the corners. So there is a quite neutral coupling. If we have to decrease the neutral coupling, we have to uh, compress the size of the resonance structure. So that is the solution for this. So I think we have you guys can how you guys can understand how to see the S parameters. I hope you are clear with the design of band stop FSS now. So, as for the application, this band stop FSS is used for radar defense application. If the band stop FSS achieves the wider reflection, it is enormously decided it is unanimously welcomed in this research field, and also as Sir said from before session, mm, we have two thumb rule. That is, one is the structure should provide polarization insensitivity, and the angle of incidence should be good. So, for polarization insensitivity, the structure should be four side symmetrical. If we divide the structure in four side, the design should be same on the edges. So that is the concept. So, some researchers have designed the FSS at polarization sensitivity due to the lack of bandwidth enhancement or shielding effectiveness. So it is so far best to design the FSS for polarization insensitivity, which gives a good welcome in this research field. I hope you guys are clear with this band stop FSS. If you guys have any doubts, you can tell me now because I'm going to proceed with the band pass FSS now. Do you have any doubts? I hope you are not. I hope you guys are not interacting. I don't know why. Let me proceed with the band pass FSS now. So similarly, you have to go to file, new and recent project template. Maintenance, planar patch and slot. As Sir said from yesterday's session, the patch is used to design the band stop FSS, which we have designed now, and slot is used to design the band pass FSS. So for that band pass FSS, we have to edge the resonator. I will show you now. Let it be same 40 to 70 gigahertz. Quickly keep with the language field and click finish. So to design the band stop band pass FSS, so it is same as band stop FSS. Additionally, we have to design the resistive sheet, and you have to etch the structure to achieve the band pass FSS frequency. So first development substrate. Same we will get to control to 3 by 2, and here minus people get to 3 by 2. Let it be 0 to T1. The material will be, so I have chosen polyimide lossy for this. So because as I said now, this polyimide lossy is a conformal substrate which can be used for military aircraft or stealth application. So that only I have chosen this substrate and click OK. So the P will be the same as band stop FSS, that is 2.3. Enter, and the T1 will be, so as I said, it is a conformal substate. So let it be 0.005. And click OK. Change the color. Okay. As I said, we have to etch this band pass FSS, achieve the frequency. Let it be resistive sheet. Minus p by 4 to p by 0 to t1. I'm sorry, into t plus t1. So the t will be 0.035. So you can see the substrate and the resistor sheet here. Substrate will be 0 to t1 and the resistor sheet will be t1 to t plus t1. So just to make a change, t1 to t plus t1. Let it be. So the height of the substrate is 0.05. So and the height of the resistive sheet is 0.035. So it is correct. Now, so I'm going to use the same crosshook to design the band pass FSS. So for that we have to run the break. Following pointers. Zero five, aluminum minus will be 1.1 and 1.1. The aluminum minus will be T1 to T plus T1 and click OK. You solve it. So similarly, we have to rotate this structure and click rotate. So you can see that the resistive sheet is placed uh, placed above the substrate, and we have also designed the resonator above the resistive layer with the same height of the resistive sheet. So now we are going to delete this to achieve the etched band pass FSS. So just click on the resistor sheet, go to Boolean, substrate, and click solid one and solid one. That's it. So the cross resonator is etched on the resistive sheet. So you can see the gap here. So I'm going to simulate. So for simulation, go to boundaries and similarly give us unit cell and change one. Change one. Click OK. So we will wait until. So you can also integrate this band stop and band pass FSS to achieve both the absorption and transmission characteristics. And to achieve that characteristics, you have to incorporate the pin diode, as I said before. So in pin diode, there will be on-off condition, where in on stage it will behave as a transmitter, and in off stage it will behave as a absorber. So this multifunctional FSS is trending research now. So many people are designing this multifunctional FSS. If you guys are interested in doing master's degree or a project work in UG, you can design the FSS, which is very valuable in this research area nowadays. So there is plenty of research papers for if bandstop and bandpass FSS, but there is a selectively less paper in multifunctional FSS. As I said, you can also integrate this both FSS to achieve that with the help of the pindiodes. So the result will be here. So we have achieved the transmission at 54.8 gigahertz. So this is the design of band pass FSS. So you can, I hope you can see the difference between the band stop and band pass FSS. As Sir said, this band stop FSS we are using patch elements to achieve the frequency response, and for band stop FSS we are designing the etched resonators to achieve the band pass response. So the FSS is also designed in variety of structures like fractal, convoluted. So you can see the research papers by using IEEE Explore. So there is many research papers for only band stop and band pass FSS, but it is a so these are very so these structures have very low novelty compared to the multifunctional FSS. I suggest if you guys are deciding to design the FSS for your project, or in case you are going to study the ME, for that you can go for multifunctional FSS. Um, so so this is the design of band stop and band pass access. Hope you are okay with the design. So now we are going to analyze the result. So we are going to analyze the angular stability, polarization stability, and there is a plenty of formula for shielding effectiveness. So first I'm going to teach you how to see the angular stability. So as Sir said, the angular performance of FSS is quite high because of the miniaturized size, which is one of the major characteristics to design the FSS. To achieve the miniaturization, the lambda value should be more uh, compared to the periodicity. So that is one thumb rule. And the FSS should achieve the angular performance as much as possible, like 75 or 80 degree. So I think the FSS is not quite stable at 90 degree. And similarly for bandpass FSS, there are many structures, then there are many constant structure to achieve the frequency for application, like radar or stealth application. So now we are going to see the angular stability for this particular bandstop FSS. And then you can control is it. So first we will see the angular stability for the first resonator, then we go for the second resonator. And do this. So to see the angular stability, you have to go for simulation, boundaries. I hope you guys are okay with these boundary condition. So the boundary condition should be unit cell, unit cell, unit cell, unit cell. So we are giving this as unit cell because it is the FSS is a periodic arrangement. And so for blockade boundaries, the Zmin should be 1. For Zmax, it also should be 1. Just click OK. And the grid angle should be 90 degree, and we have to fit the unit cell to the bounding box, which is given here. And for face angle, just click as theta. We remove and click OK. So the theta should be 0. Click OK. So I hope you guys know how to do the parameter strip. So click on the parameter strip, this new sequence, new parameters, split theta, to design from 0 to 10, let it be 20, and let's take it from 10. So there will be 3 linear. Just click start. So it takes some time to simulate this because we have given the parameters for 3 angles. I hope you guys have no any you guys have no doubts. You can also see the surface current that I will show you later after completing the simulation. You can see the result on result navigator. it has 0. Um, so as for the higher frequency, the accuracy of the angular stability will be very low compared to the lower frequency. So there is a quite disadvantage for designing the FSS at millimeter wave region. So the FSS will be so this FSS is highly used for this radar application, as I said. So the angular stability of the FSS will be quite low compare with a low frequency FSS. So this high frequency FSS have less accuracy of the angular stability compared with the low frequency FSS. So to resolve this solution, you can design the FSS with some additional resonators, and you can give the fabricated prototype with many number of unit cell elements. That is a solution for this. So it has run up to 20 degree. So there is a frequency shift at 20 degree. So this is the angular stability. So you can run the FSS up to 0 to 80 degree. So it takes quite a long time. So I am skipping this part. I hope you can understand how to how to do the angular performance in CST. So I will repeat once again. So first you have to go for simulation, then you have to go for boundaries, and obviously there is a unit cell, and for FSS you have to give a open and space, and the flockade boundaries of Z max is 1 and Z min is also 1. Click OK and just go to boundaries and click phase shift and scan angles, and just to give any constant, just theta or some other variable, and click invert OK, and just go for parameter sweep, click new sequence, and click there will be a constant which you are designing, click for theta, and from 0 to 20, and step width will be 10. You can also give us 5 or 7 or 15, it's up to you, and click OK, and you have to start the simulation. So this is the procedure for angular stability of FSS. Similarly, for bandpass FSS, I will show the angular stability. So the same process will be repeated for this also. Simulation boundaries, and just click here theta. So theta will be start from 0 like this, and go to boundaries, phase shift angle. So everything is okay. Then go for parametric speed. Click new sequence, new parameters, click for theta. So let it be 0 to gravity, the same as back stop purposes. The step it will be 10. Click OK and start the simulation. So the thinner the substrate, the lesser the bandwidth. So if you are deciding to design the FSS on conformal substrate, you have to choose the desired frequency from the allocation frequency allocation table. If you are deciding to achieve the bandwidth very higher, you have to go for rich the substrate. So it's running. We can also design the dual bandpass FSS by designing another resonator in the resistor sheet. It is quite easy. So designing the bandpass FSS is quite easy compared to the bandstop FSS. FSS. So it shows the similar performance with a slight frequency shift at 20 degrees. So it is because of the higher frequency. So whenever the frequency high, sample stability accuracy will be low. You can also verify this with the research articles on this. And there is also a slight degradation here. It is due to the harmonic loss of the substrate. So that's it. So I hope you can understand how to see the angle stability for bandstop and bandpass surfaces. And for polarization stability, you have to go for. Before that, I will add the second resonator to see the angle stability. For that, you have to go for hysteresis. Okay, so now we can see the angle stability for this resonator. And delete this one and delete the first resonator. And before simulation boundaries, the same, so completely before parameters and start the simulation. We can see a slight deviation from this resonator. So you can also add these three resonator here. The result will be same. So this resonator is responsible for the lower frequency, as Sir said. The frequency which is at the edge is responsible for the low frequency, and the frequency in the middle is always responsible for the high frequency. So, by designing the band stop and band pass FSS and by combining it with the incorporation of pin diodes, you can design a multifunctional FSS, which is a trending hot topic now. And you can also design a RAS over, which I'm doing my research in that. So it is called as frequency selective RAS over, which is known as FSR. So to design the FSS, it is similar to the to design a FSR, it is very similar to the FSS. So for that you have to design a resistive sheet. So for that you have to incorporate the lumped resistors in the design, and you have to separately design the band pass FSS to for the transmission characteristics, and you have to add these resistive sheet resistive FSS and band pass FSS with the help of air gap to achieve the frequency selective crossover. So it is also a interesting topic similar to FSS. So we have the angular performance of uh, 10, 0, 10. So no, there is only a little bit change with the slight frequency shift at 10, 10 degree. Let's see for 20 degree. So after 15 degree, the frequency is changing due to the unit cell size or the frequency response. So if the FSS is designed in very low frequency, like for 0 to 1 or zero point 0.5 to 1.5 gigahertz, the accuracy of the angular stability will be very high, like 85 degree, 75 degree, as I said from yesterday session. So if we have to design the FSS at these millimeter wave region, the angular stability will be quite low. So it is a universal truth, and people in the research area also have discussed these issues. I hope you can understand the angular performance of this second resonator. Now we can add both the first and second resonator. You can see what is the performance of angular stability here. Just upload it. Mm, Go for a canonical split. Just start this equation. So for conformal substrate, you can also analyze the bending performance of the FSS that I will show you after the simulation. And we have polarization stability and shielding effectiveness to analyze. So for shielding effectiveness, we have using the formula that shielding SEDB equal to minus 20 log of ET by EI. So there is transmission frequency by instant, that is reflection frequency. You can substitute these here. You can extract the data from here, like post processing, Voltasky, and you have save the folder, save the document, and you can convert the data into Excel sheet, and you can directly import that data into the shielding effectiveness formula. Then you can get the shielding effectiveness, which is very similar to the absorption characteristics. So it has one or two. So based on the dual frequency, it is taking quite a long time compared to the single frequency. So this I will hold for now because it is taking quite a long time. So you can, I hope you guys can understand how to do the angular performance in CST. So we have to, if you are deciding to uh, validate the performance of this FSS, you can also use ADA software as I said before. And for angular performance, you can change the angle from 0 to 80 because 90 it is not possible to achieve the ideal result. The researchers have not achieved this. Up to 85 is possible. Then just click OK. You can start the simulation. It will automatically run the CST, automatically run the FSS and show the angular performance of this design. So this is the angular stability. So as for now, I will explain. We have designed the band stop FSS by using the loop resonator, as Sir said. So this loop resonator is used to achieve the band stop characteristics. So we have designed the miniaturized size of FSS for very high frequency that cover the radar frequencies, and for band pass we have used polyimide substrate. So I have used this substrate to show you the conformal performance of these band pass FSS. So we have achieved the band pass FSS at 54.8 gigahertz, which covers the radar frequency here. And we have performed the angular stability by using the parametric sweep here. So in antenna there will be a coaxial field or some other probe field to design the structure. Here we are using the flockade boundaries because these flockade boundaries refer to the concept of periodic boundary condition, which is applied to the structure that repeats the periodicity in the free space. That's why we are using the flockade boundaries here. And so the angular stability is done. Now we can go for the polarization stability. So for that, as Sir said, the polarization step for to validate the polarization stability, we have to see the transverse electric and transverse magnetic. So for transverse electric, the theta will be 0 degree and phi will be 0 degree, and for transverse magnetic, the theta will be 0 degree and phi will be 90 degree. So I can show you guys how to do that. And go for boundaries and just click face. Just keep it as 0 as for now, and 5 is 0. So this is for TE mode. So theta is 0, phi is 0. So this is for TE mode, and click OK. Just click here and just run the simulation. So it is similar as theta normal incidence. So the TE mode is as per similar as normal incidence. So there are so many review articles in FSS. You can also um, verify the principle and what are the and also see the different type of structure used for different application. If you guys are deciding to design the FSS for your project or any other mini project or any other for internship reasons. So it has run. So the frequency is similar. The frequency response of this FSS is similar. And for transverse magnetic, we have to go for boundaries, phase shift, theta equal to 0, and phi will be your 90 degree. So this is a small change you have to do in the boundary condition to achieve the transverse magnetic characteristics. And just click OK. Wait, I will just save the result. Okay, just paste the result here. So just go for simulation boundaries and just click 90 degree and click OK. So just so these surfaces textures can be seen in Monk book as I said. So he wrote a book called The Frequency Selective Surface Theory and Design. So a lot of people designing the FSS are referring to that book, and which is quite helpful for using the equivalent circuit model or designing the FSS or enhancing the principle of FSS. You can see it. You can also get it from your library if you have any interest on studying the FSS further. So we have got the TEM mode. As I said, so this FSS is a polarization insensitivity because you can see there is no change in TE and TM mode. So it is very similar. There is no slight deviation. So this is the polarization stability. So if your structure is symmetrical, you can achieve the polarization stability. For that, TE will be theta for transverse electric, theta will be 0, phi will be 0. Similarly, for transverse magnetic, theta will be 0, phi will be 90 degree. Okay, so next we can go for surface current. I'll show you how to see the current. So okay, we will start with band stop FSS because as I told, this resonator is the responsible for the higher frequency, and this resonator is responsible for the low frequency. We can see the surface current by phone. Go for simulation, field monitor, and select H and surface current. I think the frequency is okay, 49.9. Let it be field monitor 49. Just click OK. You can see the surface current at 2D, 3D results. Perspective. Okay, as I said, the first resonator is the first resonator only responsible for the first frequency. So this uh, rectangle stub is responsible for the first frequency. As I said, the current is only high at this frequency, and for high frequency, you can also see that. So for it, so 56.4. You can also see the surface current from it. Go for simulation field monitor with H field 56.4. Just click OK and run it. So you can see the surface current for it is, you have to see the result at Z max because it is a band stop emphasis. Okay, as I said, the surface current is only higher cross loop. So this cross loop is only responsible for the high frequency, which is 56.4, and for 49.9 only the first rectangular stub resonator is responsible for it. So it is a independent structures. You can see from it. So the advantage of designing the independent resonator is if we have to achieve only the desired radar frequency. For example, from the FCC table, I have taken the radar frequency from 60 to 62.5 gigahertz. So to achieve this particular frequency, you have to design only a single resonator to achieve it. So, in case you have additional radar frequency to achieve, you can also design the second resonator in an FSS. So you can achieve both radar frequencies without any mutual coupling. So it is a major advantage of designing an independent resonators for both band stop as well as it is also applicable for band pass FSS. So, by designing these independent frequency, you can achieve the frequencies without any mutual coupling. And so, the main disadvantage I can say here is you have to go for a little bit higher. Little bit larger FSS. So it is 2.3. You have to go for 2.5 or maybe 3 to achieve the independent frequency. If you have any radar frequencies that you have fixed to design in the FSS. So these are the advantage of independent transmitters, and it is I suggest that by designing the FSS in miniaturized and rigid substrate without any conformal substrate, it is very helpful to enhance the bandwidth easily. If you guys go for a conformal substrate, it take quite a long time for optimization process to achieve the required bandwidth enhancement. If your desired radar frequency is quite low, like 1 gigahertz or 1.5 gigahertz, you can go for conformal structure and you can achieve the desired radar frequencies. If these FSS, if you are designing the FSS for stealth applications, because in stealth application there will be a vast requirement of bandwidth is necessary. So for stealth application, you can go for rigid substrate. It is very helpful. So it is depends upon the what depends upon the frequency you are choosing. So the resonators are designed in each research paper. It is depending upon their frequencies. So I will suggest to design the frequency at the particular radar frequency allocation table or any other communication frequency or any other low frequency, like sir designed an ISM band yesterday, and he have shown the unit cell and the results, right? So if you have go for any W band or shielding effective or shielding or ISM communication application, you guys have to design the FSS for low frequency, and the bandwidth requirement is not much necessary for that. If you guys are going for high frequency, like for automotive radar or defense radar application, you have to go for the FCC allocation table to fix that particular frequency, and you can design the FSS in a conformal substrate. So it is depends upon the frequency that you guys are choosing to design this FSS. I hope you guys are clear with a general idea how to design the band stop and band pass FSS. So I have. So we will summarize. So the FSS is a periodic arrangement of cells where the slots and patches are used for designing the band stop and band pass FSS. So band stop FSS, we are going for patches to achieve the bandwidth enhancement and other necessary characteristics. And for band pass FSS, we are designing the FSS by using the edged slots to achieve the characteristics. So, as I said, the independent resonator is highly recommended for designing the FSS. Because by designing the FSS with independent resonator, it will be helpful to achieve the particular frequency for any application that you guys are choosing. And for bandpass FSS, it is highly recommended to design the bandpass FSS for communication application. So, and also I forgot to say to how to see the initiation loss. So we can see -1. So the bandwidth requirement of the transmission is so minus 1 frequency range of the bandpass FSS is 51 52, almost 52, 52 to 57, and you can see the insertion loss. Insertion loss at resonant frequency. What is the resonant frequency? 54.5. It is 0.17 dB. So, if you to achieve a insertion loss very to achieve a lower insertion loss, you can also compress the width of the resonator here, or and you also can increase the size of the resonator to achieve the lower insertion loss. The insertion loss is a very important requirement. Yeah. Lower the insertion loss, higher the communication will be. So if you achieve the insertion loss very low, so it will give the transmission performance very accurately. So this is for band pass FSS, and for band stop FSS we have to see the shielding effectiveness that I have given the formula, that is SC equal to, and also sir also given the formula, that is SC equal to minus 20 log of uh, 20 log of EP by EI, which is your transmission and reflection coefficient. You can extract it from post processing, and you can import export to the Excel sheet, and you can find the shielding effectiveness for that. So if you guys have any doubt for how to see the shielding effectiveness, you can ask me. So that's it for non-stop and band pass officers. And so the evolution of FSS from the starting to end. So the researchers have designed the bandstop FSS first to achieve the shielding characteristics, and they have designed the bandpass FSS to achieve the communication characteristics. And nowadays there is a trending topic called the multifunctional FSS, where they have designed the band stop FSS at front layer and band pass FSS at back layer at the rear side of the structure. So with the help of pin diodes. So as I said, so there is a some similarity between multifunctional FSS and frequency selective resolver, which I have briefly explained now. So for frequency selective resolver, they have used a lumped resistor in the band stop FSS, which obviously convert into lossy FSS with the resistive components. So it can achieve the absorption by using the lumped resistor in FSR, we can achieve the higher absorption and transmission characteristics. And for similarly, for multifunctional FSS, they are using the pin diodes in on and off conditions. Like if it is on condition, it will be absorption state, and if it will be off condition, it will be transmission state. It is depends on the structure, and also it can be vice versa. It may be on off or off on condition. These are the trending topics in the electromagnetic uh, structures. These multifunctional FSS and these frequency selected absorber and metamaterial absorbers are the trending topic nowadays. And there is also quite papers in band stop FSS by using machine learning to reduce the parametric simulation time, as sir said from yesterday's session. So these are the trending topics. If you are deciding to uh, go for the band stop or band pass FSS, I hope you should achieve the characteristics in very novel, because you have to achieve the miniaturization, angular stability, polarization stability, which is a thumb rule for designing the FSS. And also the structure should be novel. If you have to get the good published paper, which is highly helpful for your placements. I hope you guys are in third years, it will be very helpful for your placement if you guys have any journal papers. So this session, I hope this session will be helpful for. I hope you guys can understand that how to design the band stop and band pass FSS, and I have also showed how to see the angular stability, polarization stability. Um, any doubts so far? I think you guys are not interacting. I hope uh, you guys are clear with the concept that I have shared now. Any doubts so far that I'm going to wind up the session? Any doubts so far now? Anyone? If you have any doubts, you can ask me.
Guys, if you have any doubts, please ask now.
I think they don't have a network properly, internet properly. I hope this session is recorded. If you have any doubts, you can ask me. I will be in second floor VLSA lab. I hope there is no doubts.
Ma'am, since there are no doubts, can we officially close this session?
Yeah, sure. I
Yeah.
think your classmates have no proper internet connection. That why they are not responding. Am I correct, or I'm not that much interacting? I hope I
No,
have
ma'am.
given a good concept.
You have done your part really well, ma'am. There's some network problem in the hostel, it seems. So,
Yeah.
majority are from there.
Okay. Oh, okay. So just ask them if they have any doubts, they can see me at. I think you guys know Ghulam Sir cabin. You can ask me after. I hope this session is recorded, right?
Yes, ma'am, it's recorded.
Okay. Just share with them. If they have any doubts, they can see me at the VLSA lab. Okay. I hope I'm. I hope you guys will be clear with this FSS design. Okay, shall I leave the meeting, or do you have any official closing procedure?
Yes, ma'am. Nothing much. We would like to thank you a lot for your time and effort. This was
Okay,
really
okay.
a new thing to us, ma'am.
Okay, okay.
Really
So
strong
I
and
really,
and
really, there
solid.
is a little
Yeah.
bit sad for me because I hope you guys will be very interacting because from the session which is held before, Indumati ma'am told that you guys are very interacting and it is very interesting to talk to you guys, but it is a little bit disappointing for me because I prepared a lot to share with you. It's fine.
Sorry,
It's
ma'am.
fine. It's
Sorry, ma'am.
okay.
Maybe it's due
No,
to
no,
the
no.
delay or
Just don't
something.
be sorry.
Ma'am, am
It's
I audible, ma'am?
yeah, yeah. You are audible.
Yeah, ma'am. As we are new to this topic, that's why
Okay.
there is a huge silence. I think the session was
I
wonderful, ma'am. So there is no doubt about it. So,
okay.
like, as we are new to this, we actually took some time to analyze. That's it.
I think the FSS concept was shared yesterday, right?
Yes, ma'am. But it is a short duration, right, ma'am? It's a 1 day, so we have the time to analyze.
Okay. You guys are third year or final year?
Yeah, yeah. We are in our third year, ma'am.
You guys are in third year.
Yes, ma'am.
Okay, okay, okay. Just if you guys have any doubts, you can come. You can come to the VLSA lab.
Sure, ma'am.
Okay, I hope it will be helpful for to choose your project if you guys are deciding on to do the project in AMIC EMC. Okay, okay. Can we wind up now?
Yeah, sure, ma'am.
Okay, so these guys like there is some other 13 people only here. So they are day scholars or hostel. Okay. Okay, it is a really good session to help you with the band stop and band pass FSS design. So as I said, if you have any doubts, you can contact me. So I have my official email ID, or you can come to VLSA lab if you have any further doubts. Okay, the host who are conducting this meeting, shall I leave this meeting?
Yeah, ma'am.
Okay.
You
Okay.
can.
Thank you. Thank you. Thank you so
Thank
much.
you so much, ma'am.
Yeah.